On very short notice, Professor Kate Saenko from Boston University has very kindly stepped in. So I'm very much appreciate what she's doing. Kate Saenko runs a group at Boston University which studies many things associated with domain adaptation, unsupervised domain adaptation, and she's going to talk about that right now. So without further ado, Kate Saenko, thank you.
Thank you so much for the introduction, and I'm happy to give a talk in this workshop. I actually am organizing or co-organizing a very related competition, and the live session is happening at this moment. These are very, very relevant topics. So domain adaptation, distribution shift, these are all topics that I've been working on for quite a while. What I want to talk about is adapting to novel data distribution. So this challenge was about new data distributions. What happens if we have access to data from that new distribution? That's mostly what I'll be talking about today, and that is generally known as domain adaptation techniques, as opposed to domain generalization, where you don't get to see any data from the new distribution. Right, so I think some folks already mentioned this today, and actually Rowan's talk, which was great, already mentioned some of these situations that I have on the slide, where we have a distribution shift problem. Basically, whenever your model, your neural network, your AI model is trained on some data set, and that data set is collected from, it's a sample from the world, right? And then when the model is tested on some new data, it's asked to label this new data, but this new data comes from a new distribution. For example, in this scenario, we have training data for pedestrian detection collected mostly, let's say in California, where roads are kind of clear and the weather is mostly sunny, although I heard there was something to do with smoke and some orange sky. But at test time, we might get data from, let's say, New England, where I live. I live in Boston, so it doesn't look like this yet, but pretty soon I'm sure we'll have snow, we'll have sleet, people will be wearing heavy coats. And so when the model faces such a shift in the distribution, inevitably accuracy drops. So it's going to miss some pedestrians here. And I'll note that I'll talk mostly about computer vision. Actually, the only thing I'll talk about today is computer vision applications. So image data, recognizing objects, classifying objects, those kinds of things. Okay, so this problem is called dataset bias or domain shift. I don't need to really explain it to this audience. Basically, we've been working on this for a while, and more recently, we're interested in this slight change to the setting where now you have some novel categories potentially, right? So maybe your detector had never seen a turkey before. This is something that I would see around where I live. But the detector maybe never saw a turkey, and so it has to kind of recognize that there's a novel category, and maybe it needs to do something about that. And then in combination with domain shift, again, maybe the data itself, the known categories come from a new domain or a new distribution. And in addition to that, we have novel categories, right? So this is something that maybe you might encounter somewhere, not in Boston, but perhaps in a different country, different location. So basically, I'll be talking today about not just adapting to domain shift, but also adapting to novel categories, these outliers in the new test data that you get. Okay, so what is dataset bias and domain shift in general in computer vision? I've been looking at this problem for a long time, as I've mentioned. So in this paper, this is the first time I've really become interested in it. we were trying to train a classifier of objects such as mugs and train it on data collected from the web, which is where we get most of our data in computer vision. And then we noticed that when we test this model on new data collected from a robot in a situated environment, in an office environment, which you see here, its accuracy dropped very dramatically. So this was the first time I've seen this issue of data set shift, and still trying to fix it more than 10 years later. So another kind of iconic example of this in computer vision is this game called the Guess the Dataset game. This is from a paper from Antonio Tralba and Adosha Efras from 2011, where back then data sets were much smaller and researchers could actually get a pretty decent score just looking at these examples and trying to guess which data set each example came from. And this is another way you can tell if your data set is biased, right? That you can look at samples from it and you can say, that came from Caltech 101, or oh, that came from Label Me, and you can sort of guess which distribution the image came from. And in fact, even with much larger training data sets like ImageNet, deep learning as well is not immune to this problem. So in this experiment, what happened was they trained a classifier on the original ImageNet dataset, and then they tested it on a new ImageNet test set, which was collected using the same approach as to collect the first ImageNet, but different data, but they didn't change the collection technique. But still, accuracy dropped when training on the original and testing on this new out-of-domain, but the same data collection. So this kind of shows you that even if you try to control for everything, you still might run into dataset shift. And in fact, I would argue, and I have argued, that if you have very high dimensional data like images or other types of high dimensional data, it's very hard to sample IID from your true world distribution, right? So if you have some distribution of the world, each time you sample a limited, by nature, it's going to be a limited finite data set, it's going to have some shift from the world distribution. So data sets will almost always be biased for this reason, and we just have to live with this, right? We just have to expect that we need to deal with this always, whenever we do machine learning. And in fact, this has already been something that has caused potentially real world problems. This is an example that I think Rowan also mentioned, where a self-driving vehicle hit a bicyclist because the computer vision system malfunctioned, didn't see the pedestrian, didn't stop in time, or didn't quite recognize confidently that it was a pedestrian. And according to some reports, it was basically mostly designed to detect pedestrians that are in a crosswalk, which makes sense. Most of the training data you would collect would be pedestrians in a crosswalk. So then if a pedestrian was jaywalking and they wouldn't be in a crosswalk, visually it could look different. And so it could contribute to this, well, either data set shift or this rare out of domain example. So we have to fix this if we have any hope of deploying these systems in any application that needs robust models. So, okay, what are some techniques that can help with data set bias? The first one is just augmenting the data, various kinds of data augmentation, essentially. So if all you have is your training data set, right? So you could try to augment that training data. And again, I'm talking about images. It's possible with other modalities too, but with images, you could do things like this. So for example, you could scale, do some random cropping, scaling. You can do other things like cutting out pieces of the image, introducing artificial occlusions, doing something like mix-up where you're combining two different images together, or cut mix is both cutting out and combining, and then augmix is another approach in this line of kind of more and more industrial strength data augmentation approaches. And these have been shown to be effective for generalization and for robustness to some out-of-domain distributions. Here's another example from CVPR 2021 of training image randomization, where here it's an interesting approach. They're randomizing the original image, they're augmenting it in frequency space. So you can see that the randomized image looks quite different in terms of colors, but it also preserves the semantics. So it's important when you're, of course, when you're doing this augmentation, that you preserve the semantics of your image. Okay, so what if another thing we could do, of course, is collect some label data from your target domain. And I probably, again, don't need to argue this point with this audience, but I would say that, well, we could do that, but let's just consider this scenario. So again, let's consider pedestrian detection. And in fact, let's consider segmentation. So in this problem, we have to label every pixel of the pedestrian. So we get a region instead of a bounding box. So this is a fairly expensive labeling task, right? So if you wanted to label 1,000 pedestrian polygons, it would cost you about $1,000 US dollars. And so then if you think about, okay, we also want to cover multiple poses, we want to get a coverage of gender, that multiplies our budget. Of course, if we want to also cover different ages, different races, different clothing style or weather, again, New England weather versus California weather. Finally, we want to cover very rare long tail examples like pedestrians in wheelchairs and so on. So basically what I'm saying is that it will be very expensive to get complete coverage of everything in the world in terms of labeling. Okay, so what else can we do? We could label some data. We could spend our budget on labeling. And then we could collect unlabeled data from the new distribution that we want to target, or just, it's cheaper to collect unlabeled data. It's not always possible, but sometimes it is. So this is this scenario of having labeled training data and then having unlabeled test data. And so now this becomes a problem of adapting from the training data to the test data. So we want to train the model on the labeled training data, but also transfer it to the unlabeled data, or somehow use the unlabeled data, placing some unsupervised losses perhaps on it, or pseudo labeling and things like that. So this is referred to as domain adaptation, and has a very long history of work, of course. But I'll talk about just some of our recent work in my group along this vein. So, right, so we're collecting unlabeled data from the target domain and applying domain adaptation. There are some fairly simple and fairly effective techniques that one could use here. For example, normalization can be very effective, such as per domain batch normalization can be quite effective. We could apply data augmentation to the target domain in addition to the source. We could also use semi-supervised techniques like pseudo-labeling, or student-teacher ensembling models, mean teacher. So these have also been used quite a lot for domain adaptation. And finally, we could apply unsupervised losses like distribution alignment between the two domains, and other unsupervised losses like clustering or contrastive learning. So that's what I'll talk about today. All right, so how can we solve domain adaptation? I would say in the past several years, one of the most dominant approaches that has emerged in the computer vision literature is this distribution alignment approach. So the idea here is that, okay, we have our source data set, which is labeled. So here we have some objects that we're trying to classify. And then we have some unlabeled data from the target domain. And so we're training a model, which is a deep model that has an encoder and then a classifier layer. And so what we do here is we attempt to align both the feature distributions, or sometimes also in pixel space, we try to align these two domains so that they become indistinguishable. So this is basically trying to learn an invariant representation that is invariant to the difference between the two domains, the source domain and the target domain. And like I said, this alignment could either happen in feature space or in pixel space. And in both cases, you could apply adversarial losses, right? So we can add this domain discriminator, which tries to predict which domain the sample came from. So it tries to predict if the sample is from the source data set or from the target data set, right? So just like that game I mentioned, it's trying to play that game. It's trying to guess which data set the sample came from. And then the encoder model, the one that is learning an invariant feature space, is trying to fool the discriminator. So it's an adversarial setup. Now, the downside of this approach is kind of the usual things associated with GANs, like mode collapse or cheating. So in our work, my student Dina Bashkirova showed that these models can cheat. So this pixel-to-pixel translation model is based on a GAN and tries to embed information, a high-frequency signal, to try to cheat, and doesn't always learn a good representation or good translation of the image. And on the feature side, also, we could have problems like silent failures. So here, the adversarial optimization might diverge silently. So at least with pixel alignment, we can see what the output images look like. So here I'm showing you a little animation. Hopefully you can see what the aligned source data that's been mapped to the target domain, what that looks like. In terms of features, we can't look at those as a human, so it's hard to detect divergence. Okay, but nevertheless, the earlier works, or I should say kind of the earlier deep learning works for visual domain adaptation, all try to do this kind of alignment. And here you can see training. So the top row is the training data set, the bottom row is the test data set. So if we train and test on MNIST, of course, we get very good accuracy, 99%. But if we train on, let's say, these SVHN digits, which are street view digits, and test on MNIST, we see a huge drop in accuracy to 67%. So of course, that's terrible. And you can see even in smaller shifts, like from USPS to MNIST, you have a similar drop in accuracy. But this domain alignment technique here, it's illustrated from the work by Gannon at ICML 15. It takes the source and target distribution here shown in blue and red and aligns them together so that now the two domains are indistinguishable. And so the hope is that the classifier trained on the source data generalizes well now to the aligned target data. And in fact, this does work on these digit benchmarks. Even back, in 2017, roughly, we see pretty good gains, right? So mostly not fully closing the gap at this point. I would say that gap has been very close to close, very, very close to solved for these digit benchmarks. So the takeaway here is that domain adaptation can improve our accuracy on the target data even without any labels, right? So we had no labels from these target data sets. We just had access to the unlabeled data. So you can think of it as a form of unsupervised fine-tuning, right? Using this adversarial loss. And similarly, in feature space, this is a paper called Cicada, where we are aligning either driving images from a game to the real world. So on the left, you see the game image. On the right, you see that game image taken from the Grand Theft Auto game, aligned, projected into the real world domain using a real world data set called Cityscapes. And then on the bottom, you see a similar result, but for the digit domains. So here the takeaway is that we can do this also in pixel space. And essentially what this does is it matches the style of the source to the target, right? So it kind of looks like a style transfer technique. And speaking of data sets, so in my group, we have been collecting data sets for this problem of domain adaptation for visual data. The first data set was called Office 31, and you can see here the improvement on this data set. So the average accuracy from 2016, this is already 6 years after the data set was introduced, but it was around 76%. Right now it's up to sort of low 90s, possibly even higher at this point. So quite a lot of progress on this data set. This data set is small by today's standard. Now, another data set we've collected is called VISDA, which is a simulation data set. So the source domain is simulated and the target is real images. Also, there was quite a bit of progress on this data set in the last few years. And then, finally, we collected a larger data set called DomainNet. So here we have almost more than 500,000 images and 6 different domains. So the domains are, for example, clip art or real photos or sketches. And here the accuracy is still quite a bit lower because the number of categories is very large. It's much larger than these other data sets. So I would say that this is still an unsolved, ongoing benchmark. Now, I also want to mention the WILDS data set. So this was very recently released by Ko et al. Originally as a domain generalization data set. And this is not only images, so you can see here the different domains. The goal here was to have a data set kind of in the wild that had different distribution shifts. But you see some images from a wild cam of animals. You also see some hospital domains, some healthcare domains, some satellite domains, and non-visual domains as well, like online comments or product reviews. And very recently, this is literally not quite an archive yet, but will be very soon. This data set was extended to also contain unlabeled target data. So now you could do domain adaptation on this data set, not just domain generalization. Great. Okay. Andre, maybe you can tell me if I'm getting close to the end, just so that I can wrap up.
You're still, I think you're still good to go. I mean, okay. Going for like another 15, 17 minutes would put you well within our original time budget.
Okay, sounds good. All right, so let me talk about some of our approaches, more recent approaches, I should say. So more recently, like I said, I've been interested in this issue of novel categories. So here we have not only a shift in the input data distribution, but also in the label distribution. So the distribution over the labels Y at training time may not match the distribution at test time. So this means that we could either have missing categories or novel categories at test time. And so we need to deal with that. In this paper, we looked at this scenario where we have these source and target labeled and unlabeled examples. And then we have some categories that are either only in the source or only in the target. So these categories are shared. This is a source-only category. This is a target-only category. And so now if we want to do domain alignment, it's not going to work well because it will, by default, try to align these different categories together because they shouldn't be aligned together. And so the approach that we went with here was more based on clustering and self-supervised learning rather than domain alignment. So the idea is first we find neighbors in the unlabeled data, and we compute the probability that I is a neighbor of J for every unlabeled point. And then we minimize the entropy of this probability. So this essentially tries to learn a representation that clusters data and tries to take advantage of natural cluster structure in the target data. And this can be done without any labels, of course. And so once we've done that, we also perform entropy separation to try to reject the outlier classes in the target while aligning the shared classes with the source, right? So these crosses and circles should be aligned together. They're shared classes, so we can transfer that knowledge to those classes. But the triangles are a novel class, and the target we don't want to transfer to that class because we don't have any labels for it. We just want to reject it and say that's an outlier. The model should just say, I don't know what to do with this, right? So in the final feature space that we obtain, we hopefully have this picture where we've aligned the shared classes and rejected the unknown outlier classes in the target. And so I want to show you this example of this scenario where we have a shared class and novel class and standard alignment breaks, right? So here the shared class is the strawberry. There are two domains here, the real photos and sketches, these drawings. We're trying to transfer knowledge between them. And then in the source and the real images, we have some classes that don't appear in the sketches. So clocks, for example, they don't appear in the sketch data. And so after standard alignment, this catastrophic alignment happens where a strawberry gets aligned with the clock class. Because again, we're just here, the objective is just to make the two distributions the same. And so that's what ends up happening. With our approach, we call it dance, by the way, we don't get this problem, or not as much at least. We avoid it for the most part, where here, for example, this clock doesn't get aligned with any of the target classes, any of the target samples. So this is the situation that we want to see. Okay, so I just told you that we can do this. We can improve domain transfer using essentially in-domain self-supervision, right? So this is self-supervised loss that tries to cluster the target points. What if we also did that, but we placed the constraints across domains? So we call this cross-domain self-supervision. And this is an ICCV 21 paper where we do something similar. We find nearest neighbors, and then we try to push those neighboring points closer together. But now we look for neighbors in the other domain. So it's a cross-domain contrastive learning objective. Right. So again, the ideal case that we hope for is that the shared classes become aligned, but the novel classes are still rejected or kind of moved away from the shared classes. And so this can be seen as a pre-training step where we then take the resulting representation and use it for any downstream task that we might have. Like we could use it for domain adaptation, for retrieval or few-shot learning. But basically, if we have some unlabeled multi-domain data, we can use this pre-training step essentially. Or even if we have an existing ImageNet model, which a lot of the time we start with an ImageNet trained model, we can fine-tune it this way without supervision on multiple domains. All we need is the domain label. We just need to know which image came from which domain. We don't need the class label for this. And so we show that if you do this, you can actually get improvements on several tasks. Like here, we are evaluating domain adaptation. So here we have novel categories and distribution shift, as I mentioned. So we're evaluating both the H-score, which evaluates how well we're rejecting outliers, and class accuracy, that's for the inlier classes. So class accuracy. measures how well we are classifying the known classes that are labeled in the source, but how well we're classifying it in the target data. So this is just nothing if we do nothing. If we apply some of these standard adversarial alignment techniques, you can see here, they don't work as well. Some of them do improve a little. With our dance approach, we get better performance on class accuracy, but not so much on the rejection. But with this pre-training technique I just described, we have much better results on rejecting the outliers and also improve accuracy. So trying to essentially improve on both of these metrics, right? We want to measure both inlier accuracy and outlier rejection. And so this outlier rejection becomes quite important, right? So in fact, it brings up this question of how do we know if a class is a new class or something that we've seen in training time, right? So we want to reject these new classes because we don't want to transfer models to them. So here, we of course know that these are monkeys and not people, but to the algorithm, these might look similar. So the algorithm needs to know, okay, should I transfer it? Should I label this as a person or should I label this as an outlier new class? Of course, that always depends on the application. Maybe it doesn't matter. If you're a self-driving car, you still want to stop the car. But if you really care about accuracy on the source classes, you need to solve this problem. And so we've also recently looked at this problem more and how to reject novel categories and came up with a pretty simple approach. So here we just train K one versus all classifiers as opposed to training a softmax classifier, where we treat one class as the positive. So these are all the training classes that we know about. These are inlier classes, right? So we train a one versus all. So each classifier treats one of the classes as positive and all the others become negatives. And so we train K of these classifiers essentially. And then anything that these classifiers do not detect above a threshold, we call all of that unknown classes. So we do rejection of outliers. And so again, what we want to do is we want to train these open set classifiers on the labeled, these are labeled source points. Then before adaptation, here I'm showing also with unlabeled target data, the one versus all classifiers are shown with dashed lines. And so now we can reject these new classes like the stars are outlier classes that we want to reject and hopefully end up with a picture like this after additional alignment. So we do apply some entropy minimization here. And on this office data set that I mentioned before, we do quite well across a range of numbers of unknown classes, as you can see here. And also that's an accuracy and H score also. So blue line is our OVA or one versus all network. Accuracy is also quite a bit better than some of the other techniques. And I want to mention that actually this problem is very related to another problem of semi-supervised learning with novel classes, where in semi-supervised learning, we may not have a distribution shift between the labeled and the unlabeled data, but we might have a distribution shift, in fact, in some applications. So that's basically the difference between these two problems. And so I'll just skip over this very quickly because I think I'm close to out of time, but we have some work on essentially applying these techniques and new techniques to the semi-supervised learning problem, where we want to learn from labeled data and unlabeled data that has outliers. So the unlabeled data is hard to control. It might have outlier classes. And so in this paper, we try to approach this problem. And the key here is to separate the inliers and outliers again, and then only compute the semi-supervised loss for the unlabeled data, which we deem to be inliers, or deem to be known classes. So there's a lot of course, work in semi-supervised learning. Pseudo-labeling and particular fixed match have been quite successful recently. So we start with this, we take this model as kind of the base, and then we improve, we add outlier rejection to this model, so that when we compare to various baselines, we have improved performance that I'll show you quickly. But basically, the new idea is to start with fixed match, which is only applied to pseudo-labeled inlier classes. And then we add an outlier detector based on our one versus all network. We also add a consistency regularization loss on this outlier detector. And this gives us state-of-the-art performance on OpenSet SSL. I'll skip the slides, just some more details on the consistency regularization. But here are some results. In terms of outlier detector, you can compare the performance of fixed match with our method. Fixed match, of course, doesn't do outlier detection, and our method is essentially fixed match after outlier detection. You can see the big difference that you have in performance. And we also see improved outlier detection compared to state-of-the-art outlier detection methods because of this consistency regularization loss. All right. I'll skip this. I'll just mention very quickly that we put together a challenge around this problem of domain adaptation with outliers, where we might have novel classes or might have missing classes as well in the target domain. And if you're curious, you can check out our work. Well, our workshop is happening right now. You can check that out, but you can take a look at the recorded videos, which will be posted later, to see what the winners used and what the results were. And I'll wrap up to just say that robustness to distribution shift is a long-standing problem, very important problem. It's still mostly lacking, I would say, in computer vision, although things are getting better, but I would say that for the most part, it's still an unsolved problem. And this universal adaptation setting where you could have missing or novel categories is traditionally been less looked at, but I think it's also important because we often just don't know what the unlabeled data holds. And finally, OpenSet SSL is a related problem that I mentioned at the end there. And a lot of the techniques can actually be applied to both of these setups, domain adaptation and semi-supervised learning. Open questions. I think this is my last slide. Just some thoughts for the future. I already mentioned we need to know how much distribution shift is too far. At some point, we need to decide this is not a class we know about, it's something new. What happens if the outliers are very similar to inliers? Like here, a seagull might be a known class, but an eagle is a novel class, but they look very similar. And then we also need to know how to tune hyperparameters if we don't have any labels in the target domain, which is a difficult problem. And of course, if we have no access to the target domain, we need to know how to generalize, right? So nothing that I talked about today really addresses this problem. All right, I'll stop here. I'll thank my students and my sponsors, and I'll take any questions if there's time. Thank you very much.
Hi. So thanks for this very interesting talk. So I'll just open up with a couple of questions, and then we can have more questions from the audience if there's any. So a lot of this is so like they're loaded questions coming from me, but so all of this is mostly about images. Could we, like, how difficult would it be to adapt these methods to other domains and perhaps other image tasks? So not just classification, but like segmentation or depth estimation and other stuff. That's the first question. And the second question is, are there any obstacles to scaling these methods to industrial scale tasks in images?
I think that yes, we can apply these techniques to other data. The distribution alignment technique is very generic, especially in feature space. So if you're aligning distributions in feature space using adversarial learning, you can apply that to anything. In the input space, I showed you these results of aligning images, of translating images from the source domain to the target, like changing the style, like changing the kind of the style of the visual domain. I'm not sure if that's applicable to other types of data, but yeah, I think a lot of the other like a lot of these techniques are basically either borrowed or very similar to semi-supervised learning techniques like entropy minimization or adversarial entropy optimization or meme teacher or these ensembling pseudo labeling methods. The only thing is they all assume they have access to unlabeled target data. If you don't have unlabeled target data, then I think you're having to do a lot of data augmentation, and that is a domain specific, like it's a modality specific thing. I showed you for images you can do cropping, you can do color transforms, but of course for other modalities you need to do something else. You need to come up with some other data augmentation technique that preserves semantics in that domain. In terms of scaling to industrial tasks, yeah, I think it's possible. I don't think anything here is extremely prohibitive. Maybe one issue that would come up is, you need to collect this unlabeled data and then adapt to it, and that takes some time as well. So even though it's less time than labeling it, but it's still like if you have a production system, it still introduces a delay because you need to retrain it essentially.
Okay, thanks. Yes, I guess that all makes sense. There's a question from Ivan Bondarenko about can zero-shot learning approaches such as CADA VAE help to address domain adaptation? If you know what CADA VAE is.
I'm not familiar with that paper, but in zero-shot learning, you assume that you have no training data at all. And in domain adaptation, you always assume some training data in the source domain. So I think those are more complementary techniques. So you could combine it with, you could transfer knowledge of known categories that you have labeled data for, and then you can also try to apply zero-shot techniques for categories or tasks that you have no data for.
Right. Another question is, how well do distribution alignment methods work for really similar data sets with not so obvious distribution shift based on human observation? For example, ImageNet to ImageNet v2.
That's a great question. So I would actually love to know, but everyone I've asked so far hasn't tried that experiment. I would love to actually try these techniques on ImageNet v2. My guess is that it might not work if ImageNet v2 in fact contains some very difficult examples. So for like very rare type of an object or very strange pose, for example, there might just be hard examples. But if the domain shift is maybe more subtle, maybe it's just slightly different poses, slightly different lighting, or slightly different backgrounds, I think it should work. But yeah, I don't think I've seen that result.
Right. Are there any other questions? So do contrastive and clustering methods for domain adaptation work when we get examples in an online fashion? Meaning we don't know beforehand that we have X number of domains, or that the data points in the domain are not static and change over time in a way smoothly moving in between domains.
Yeah, thanks for that question. I think if we don't know which domain the sample comes from, these techniques could still potentially work, although, yeah, so we don't actually need to necessarily know the domain label, right? We could just look for the closest example and try to align it using contrastive learning. So I think it might be applicable in this situation. But yeah, it's an interesting setup, and I haven't seen really too many benchmarks in vision that have this property of like an infinite number of domains that you don't know which one is which.
Right. So there's another question. Can you contrast your problem formulations with OOD and open set paradigms?
Yeah, that's a great question. So OOD is out of domain detection, right? So open set is when you have an open set of categories, so that at test time you might have a novel category that you don't have a label for. And so in our problem formulation, we have this open set situation where we need to essentially reject the outlier class, but we also have a domain transfer setup where we have some labeled classes in the source, and some of them, although not all of them, might appear in the target data, which is unlabeled. And we want to transfer that knowledge from the known classes in the source to the unlabeled but shared classes in the target, while rejecting the novel classes. So the example I gave earlier was, we have a pedestrian detector, so the known class is pedestrian. And now we've trained it on some labeled data of pedestrians in California, and now we want to adapt it to unlabeled data from New England. But now we also have turkeys, and turkeys are not pedestrians, and we don't want to label them as pedestrians. So we want to reject them instead of transferring the classifier to those samples.
Could I just follow up? So the other, yeah, I mean, I totally understand your answer. It seems that another aspect is that the tradition in OOD and OpenSet is that you're only allowed to look at one image at a time, and you have to make your decision right there. Whereas in the domain transfer case, it's more like semi-supervised learning, right? Where you have this unlabeled data, and so you can analyze it kind of as a group, which I assume makes it easier to identify the novel classes and so on. But of course, the thing the OOD and OpenSet people do not have is that there is a domain shift as well. Between so yeah, from my perspective, you're kind of combining. You face the problems of simultaneously of domain shift and OpenSet, but which makes it harder. But you have the advantage of doing a sort of batch analysis of a bunch of data, which maybe makes it easier. Do you think that's an accurate characterization?
Yeah, exactly. No, that's a great way of putting it as well. Yeah.
Okay.
Yeah,
Thanks
it's
for the lovely
both
talk.
harder and easier.
Yeah.
Good.